Hello, this is the next video in a playlist that I'm calling Correlation. I'm also going to put this in my non-parametric playlist. And we're going to look at Spearman's rank correlation. And it's a non-parametric procedure that measures the correlation between two bivariate variables. Now, as a reminder, the zero-order correlation, or just commonly called Pearson's correlation, is between bivariate variables distributed with some distribution. Now, the population correlation is the covariance divided by the product of the standard deviations. And since it's population, we have to let it equal some Greek letter, and it's typically by rho. Now, the sample correlation, and specifically the Pearson's correlation, is the sample covariance divided by the product of the sample standard deviations. Now, typically you divide that by n minus 1 on both, but those cancel and we're just left with this formula. Now let's explore the idea of ranks. So let's take a sample of size 4. Remember, they come in tuples, so x1, y1, x2, y2, etc. And let's assume that we get 4, 5, 1, 3, 7, 2, 2, and minus 1. Now these are what's called variate values. They're actual, that's our data. That's the values of our data. And the way that we rank these, we rank them within the x's and then we rank them within the y's. So if we just look at the x's, this is the smallest, then that, then this one, then this is the fourth. Now we do the same thing for the y's. So this is the smallest, second, third, fourth. So these are the ranks of our data. You know, it's the marginal range. So now in Pearson's correlation, we use these variate values in this formula. Now if we use these ranks in this formula here, that's exactly Spearman's rank correlation. We just based the correlation on the ranks of the data. The ranks of the data. And that's it. And we can end the formula or the video there because that describes it exactly. But I want to derive maybe a formula and give you a little deeper understanding. So now let's look at the difference of these ranks. So 3 minus 4, 1 minus 3, etc. Those, we're going to call those DI. So that's the difference in the ranks. And generically, we write it RI minus SI. So RI, SI. You take that difference and we come up with these. Now, it would be nice, and it's going to be computationally easier to base a formula on these differences than the actual the rank-based values for this formula. And that's what we're going to derive. So the RIs are the rank of the X's, the SIs are the rank of the Y's. For example, R1, that means the rank of our first observation, which is 3. S3 would be the rank of our third Y, which is 2. Anyway, that's kind of how notationally what we're going to use. So Spearman's correlation is this. It's the zero-order correlation with the ranks instead of the variate values. Now notationally we have to do it like this. So instead of xi, we use ri because that's the rank of the x's. And this is the mean of the ranks. Si are the ranks of the y. And this is the mean of the y's, and the same thing down here. Now these two formulas are 100% same, but we use the variate values and we use the ranks. Now, in what follows, I'm going to pass you off to a video that I call Summation Formulas for Integers. And if you haven't seen it, I'd recommend it because the formulas we derive in there are going to be so useful, especially if you want to delve into more of the theory of non-parametric statistics. Let's go through a couple of these. So the sum of the ranks of the x's. Now, one thing to remember is we're sprinkling down a permutation of the integers 1 through n. So here we have n is 4. So we're going to use the numbers 1, 2, 3, 4 and assign them to the value. So it's a permutation, 3, 1, 4, 2. And we do the same thing with the x's. We sprinkle down a permutation, 4, 3, 2, 1. So really, we're using all those integers. And so if we look at this here, if we sum the ranks, really we're summing the integers 1 to n, right? That's what this formula recommends. And the same thing for the y's. We're really just summing the integers, but it's, we call them the ranks. And to sum the first n integers, there's a famous formula here, n plus 1 over 2. Now the mean of the ranks of x is really the mean of the sum of the first n integers. So you divide this by n, cancel with that n, you get this. Same way with the mean of the ranks of y. It's really just the sum of the integers divided by n. Now this formula, for more detail, you need to really watch that video. But the important part here is that this is equal to this, which is equal to this. That's the important part. And if we think about just these first two, the only thing that's going to change on each index or increment is rank, the Ri. Now, so there's going to be n terms, and in those n terms, there's a value of 1, a 2, a 3, all the way to n. And so we could rearrange those so to make the first rank, a 1 and then a 2, and they can go in order, and that's what this represents, right? Because R bar is this. And the same here, those three formulas are equal. And in that video, we derive that it's equal to this. Now, we need to get a little hold on the squared differences, and that's what our formula is going to be based on. So the sum of the squared differences, which we said was this, the rank of the x value minus the rank of the y squared. We're going to add 0, subtract the mean, add the mean. So we're adding 0, doesn't change it. Now let's square this. So this squared plus this squared, and then that times this times that. There's 2 of these. Let's take this piece to the other side and then take that back over here and then divide by 2. And we get this. So this piece is here. Those which are this, boils down to this, and then that sum becomes a negative, but then we divide it by 2. Now here, this formula represents a ranking like this. So the x's would be ranked 1, 2, 3, all the way to n, and minus, and this represents if we rank the y's from n to n minus 1, n minus 2, all the way to 1. That's what this represents. And actually write a few of those out and make sure that's right in your mind. So then this combines to 2i in minus n plus 1. If we factor out a 2, it has to come out squared. That's why there's a 4. But then we get a divide by. And this piece is that. So we get this value. So the 4 cancels with the 12, becomes a 3. So now if we look at Spearman's correlation, the numerator was exactly this. So we're saying it's that. The denominator was actually the product of these, which is this. So it's this squared, square root, so you get it back, which is this. Now divide that, divide this. This is the formula that's often quoted in a lot of books. It's the sum of the squared differences. Computationally, much easier to do. Now, let's see if this behaves like Pearson's correlation. Pearson's, if it's a value of 1, we have an exact linear relationship with a positive slope. If it's negative 1, Pearson's correlation, we have an exact linear relationship with a negative slope. Let's see if Spearman's correlation, which is this, behaves similarly. So let's assume there's sort of perfect positive rank correlation. And that means when we rank the values, the x's and the y's have the same rank, right? So it's an exact line using the ranks. Now the actual variate values may be a little bit different, but we're calculating rank correlation. So the differences, the sum of the square differences is this. That's 0, which means this is 0 and that's 0, and we get 1. So if there's perfect positive correlation, Spearman's correlation is 1. So it's very similar to Pearson's correlation. This is Spearman's. So perfect negative rank correlation, it means that they get ranked exactly opposite. So the x's go from 1, 2 to n. The y's go from n minus 1 down to 1. So if we were to add the ranks of each pair, they would add to n plus 1. And write out a few of those, make sure that's right in your mind. But I note this because if we were to take this r to the other side, then we get a value or a formula for s in terms of r. So if we look at the sum of these square differences, which is r minus s, but s is n plus 1 minus r, then this can combine to this. And remember, we're adding up terms. The only thing that changes is this, and integers go in there, so we could rearrange that. And this formula is this, where we're just summing the integers. But this is something that we calculated up here. So we could put the sum of what it equals into this formula. And that's what we do here. Those reduce to minus 2 and we get minus 1. So perfect negative correlation is minus 1, and that's very similar to what we'd get in Pearson's correlation. So anyway, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Now, one additional thing I'm doing is I'm putting the notes for this video on something called Gumroad. And if you look in the description, you can click on it and then go view the notes and download them if you want. Well, that's all I have. Like the video and subscribe so you don't miss the next one. Thanks. Bye.